Hey everyone, welcome to this explainer. We are unpacking a genuinely massive piece of AI news today. Google just dropped an experimental 26 billion parameter mixture of experts model called DiffusionGemma. And honestly, what makes this so exciting is that it completely flips the script on how text generation actually works. We are literally shifting away from a memory bottleneck paradigm into a raw compute paradigm. The result? An incredibly fast, highly parallel approach to generating language.
So here's our roadmap for today. First, we'll look at the autoregressive speed limit. Second, the printing press paradigm. Third, we'll look under the hood at text diffusion. Fourth, we'll compare the fusion to speculative decoding. Fifth, deployment with NVIDIA NIM. And finally, we'll wrap up with a reality check and some trade-offs.
All right, let's jump right into Section 1, the autoregressive speed limit and how we are hitting the memory bandwidth ceiling.
Okay, let's dive into this. To really understand why this is such a breakthrough, think about traditional autoregressive models like a vintage typewriter. They generate text sequentially, right? One single token at a time, moving strictly from left to right. It is a completely memory-bound process, which, let's be honest, can really test your patience when you're just sitting there watching tokens slowly trickle across the screen. DiffusionGemma, on the other hand, it operates like a massive printing press. It drafts 256 tokens entirely in parallel, making it compute-bound rather than memory-bound.
The absolute crux of the issue here is the VRAM bottleneck. In a standard model, every single generation step forces the system to move parameters from your VRAM over to the compute units. And because system memory usually isn't as blisteringly fast as enterprise high-bandwidth memory, the processor ends up spending a massive amount of time just moving data around. Your expensive GPU compute cycles are literally sitting there idle, just waiting for the memory to catch up. So memory bandwidth becomes a hard, frustrating ceiling on your speed.
Which brings us to Section 2, the printing press paradigm, and how we bypass that bottleneck with parallel generation. Let's look at how Google shifted this bottleneck away from memory entirely, pushing it over to raw compute power so you can actually maximize your hardware. 1,000 plus. That is the staggering number of tokens per second DiffusionGemma achieves on a dedicated NVIDIA H100 GPU. And it's not just for enterprise racks. Even on a consumer-grade NVIDIA GeForce RTX 5090, it hits over 700 tokens per second. By generating text in parallel, this new architecture delivers up to 4 times faster inference compared to standard autoregressive processing.
I absolutely love this quote from the source material because it just paints the perfect picture. It upgrades your model inference from a single sequential typewriter to a massive printing press that stamps the entire block of text simultaneously. By feeding the processor a much larger chunk of work all at once, literally 256 tokens in parallel, DiffusionGemma ensures that your hardware is being fully utilized instead of just twiddling its thumbs waiting for the next sequential keystroke.
So moving on to Section 3, under the hood, text diffusion. What are the actual mechanics of generating text in parallel?
You might be wondering, how does a language model actually stamp out an entire block of text all at once? Well, let's break down the engineering here. You know how AI image generators start with a blurry, static-filled canvas and slowly clear it up until you get a crisp picture of, say, a cat riding a skateboard? Diffusion-based text generation applies that exact same logic, but to language. It starts with pure noise and iteratively refines it into clear, coherent text.
Here's how this builds across 3 very deterministic steps. First up, canvas initialization. The model starts with a blank canvas of 256 random placeholder tokens. Second is iterative refinement. The model makes multiple forward passes, and as it locks in the correct tokens, it uses those as context clues to denoise the rest of the placeholders. And third, we have bidirectional attention. During every single pass, each token attends to all the other tokens. The model sees the entire structure at once, not just the stuff that came before it. Now, what's incredibly fascinating are the new behaviors unlocked by that bidirectional attention. Because the model isn't reading blindly from left to right, it can flawlessly close out complex markdown formatting. It can generate an infill code in near real time. It can even intelligently self-correct its own output during those refinement passes. The open source community, folks like Unsloth, have even fine-tuned it to play Sudoku. That's a logic task standard models really struggle with, simply because in Sudoku, future tokens heavily dictate the past tokens.
Section 4, Diffusion versus Speculative Decoding. Let's map out Google's optimization landscape.
And this brilliantly illustrates that DiffusionGemma isn't Google's only recent play for speed. They've given us 2 different paths.
Gemma 4MTP uses a tiny 74 million parameter drafter model to rapidly guess future tokens, which the main model then verifies. It's basically a really clever way to speed up the traditional typewriter, giving you up to a 3x speed boost with literally zero quality degradation. DiffusionGemma, though, abandons the typewriter completely for the printing press. It's up to 4x faster and optimizes for raw compute efficiency, but it changes the fundamental nature of how the output is generated.
On to Section 5. Deployment with NVIDIA NIM. How do we integrate DiffusionGemma into real-world applications?
So, for the developers watching, how do you actually get this running? Google explicitly optimized this 26 billion parameter mixture of experts model for NVIDIA hardware. It's super smart. It only activates 3.8 billion parameters during inference. You can grab the weights directly from Hugging Face under a highly permissive Apache 2.0 license. From there, your cleanest path is deploying via NVIDIA NIM. NIM gives you these great zero-setup containerized microservices that expose OpenAI-compatible APIs. That means you can just drop DiffusionGemma right into your existing chat or agentic workflows without rewriting all your routing logic. And if you need to customize it, you can use the NVIDIA NeMo framework to fine-tune specific pathways within the MOE architecture without having to retrain the whole shebang. But developers, quick heads up here. You are definitely going to need a UI adjustment. Because of the parallel diffusion process, you aren't wanting to get a continuous, single-token stream like you're used to with autoregressive models. Instead, you'll receive batched chunks of tokens. So your front-end renderers absolutely must be updated to buffer and handle these batched arrivals, managing the partial syntax until the whole diffusion process converges. Let's wrap up with Section 6, Trade-offs and Reality Check, understanding the constraints of experimental models.
It's time to ground this explainer for a minute. This is a bleeding-edge experimental model, right? So we have to ask, what is the catch? Let's pivot and look at the actual practical constraints of adopting an experimental diffusion text model today.
Here are the practical limitations you really need to be aware of. First, iterative overhead. Yes, it processes 256 tokens simultaneously, but the total time it takes heavily depends on how many refinement passes your specific prompt requires. Second is hardware dependency. Right now, this is highly optimized for NVIDIA platforms only. Third, memory constraints. If you want to fit this 26 billion parameter model onto a high-end consumer card with an 18 GB VRAM limit, like an RTX 4090 or 5090, you absolutely must use quantization. Full precision is going to require enterprise hardware. And finally, because this architecture prioritizes sheer speed and parallel layout, the overall output quality is just going to be lower than standard autoregressive Gemma 4 models. So, with all that said, what's the exact target use case? DiffusionGemma is custom-built for interactive local workflows. We're talking rapid inline editing, near real-time code generation, and complex nonlinear text structures. It's for those specific applications where sheer parallel speed and structural coherence are vastly more important to you than the strict, predictable, sequential reasoning that standard LLMs provide.
We've seen today exactly how shifting the bottleneck from memory bandwidth to raw compute can unlock massive speed gains. As we make this shift from sequential typewriters to parallel printing presses, how will diffusion architectures redefine your real-time AI applications? I highly encourage you to go check out the developer tools like NVIDIA NIM we talked about today and explore this for yourself. Thanks so much for joining me on this explainer, and keep innovating.